Hello and welcome. In this video we want to take a look at one last theorem for this course. It is called the Divergence Theorem. And I want to put it in some context here. We've been working a lot lately with integrals that relate stuff going on the inside with what's happening on the boundary. I mean, it's all started back in Calc 2 with the fundamental theorem of calculus that says when you integrate the derivative of a function from a to b, that's just equal to the function evaluated at b minus the function evaluated at a. It was just the endpoints of the integral that made any difference, right? In this course, we then saw the fundamental theorem of line integrals that says if you've got a function f and you're looking at the gradient field of f, then the line integral along a curve, this could be in the plane or in space, of the gradient of f dotted with dr, so that's the line integral of the gradient along the curve, that's just equal to f of b minus f of a, where b and a are the starting and ending values of the parameter to get you from one end of the curve to the other, right? It looks a lot like the fundamental theorem of calculus. It's just that instead of integrating over a straight interval, you're now integrating along a curve in the plane or in space. Okay. Then we moved on to Green's theorem, and Green's theorem was the double integral over d of q sub x minus p sub y dA equals the line integral around the boundary of d of p dx plus q dy. So let's specify here that this capital vector f here is the vector p comma q, and so this line integral f dotted with t ds, that's the line integral of f along the curve, sometimes written this way. I'm using, I don't know where that c came from. I'm using partial d to mean the boundary of the region d. C is also being the curve, which is the boundary of the region d. Right? So the line integral here is along the boundary of the region, and it's just dealing with the function, the vector field f, where the double integral, which is over the inside of the region, involves q's, a partial of q with respect to x and the partial of p with respect to y. So these are partial derivatives of the component functions of f. And this was just in the plane. Stokes's theorem then bent that into double integral over a surface. And this is the curl of f dotted with ds, so surface area there, and that's equal to the line integral around the boundary of the surface of f dotted with dr. Okay. Now notice that the curl of f, when you reduce it down to a 2D vector field, just looks like partial of q with respect to x minus partial of p with respect to y, and that's times the vector k, or minus k, actually times the vector k. If this turns out to be negative, then it would be minus k, just by default. Q sub x minus p sub y is the two-dimensional analog of the notion of curl here in 3D. Okay. So Stokes's theorem is very much like Green's theorem. We then had a different version, well, actually this came before Stokes's theorem, but we did have a different version of Green's theorem, which was called the Flux version, where the double integral of p sub x plus q sub y dA was equal to the line integral around the boundary of minus q dx plus p dy, which is just the line integral of f dotted with n ds. So this is the normal vector to the curve. So this is not it's not the vector field along the curve, it's the vector field across the curve, and we call this the flux. This was the flux integral. And it was related to the double integral of partial p with respect to x plus partial q with respect to y. And remember, that is the notion of divergence in the plane. So the line integral of the normal component of the vector field was equal to the double integral of the divergence, whereas the line integral of the tangential component was equal to the double integral of the curl. So we have the 3D equivalent of Green's theorem original version. Now we're going to have the 3D equivalent of Green's theorem, the flux version. And that's what's called the divergence theorem, or sometimes called Gauss's theorem. Now, get everything visible here. Let S be a piecewise smooth closed surface that encloses a solid E. Assume that S is oriented outward, and let F be the vector field PQR with continuous partial derivatives on an open region containing the solid E. Okay. Then the triple integral of the divergence of this vector field F is equal to the surface integral over the boundary of the region E, dotted with ds. There should be a dot in there, and I'm going to change it. Hey, Editor Will here, jumping in while I'm changing that, putting that dot in there. I want to point out that I don't know how to do this to get it to print this way, but I really want to have a circle around here. And we had the notion up here of a line integral around a closed curve, right? Start and end in the same place. This surface is a closed surface, right? That it doesn't have a boundary. It is the boundary of the solid E. And so I really want that double integral to look like it's got a big old circle in there, but I couldn't find the right notation to get the computer to draw that circle in for me. So this is like a line integral around a closed curve. This is a surface integral around a closed surface. Okay, now back to the video. Yeah, a dot should be there. Remember that this D vector capital S is, it takes into account the unit normal vector, which we often call capital vector N, right? And a little bit of surface area element, okay? And so that looks very much like this here, this NDS, where this lowercase s was just used as a little bit of surface area. No, this was a little bit of, sorry, this was a little bit of arc length here, and now this is a little bit of surface area, but both times the normal vector n, and then dotted with the vector field. Okay. And the divergence of f, right, would just be partial of p with respect to x, plus the partial of q with respect to y, plus the partial of r with respect to z. So it's very much like that, with just one more component involved. Now, the proof here, again, I should probably have this in quotes because I don't know if this is completely rigorous, but at least the idea of the proof is to subdivide the region E into a bunch of little squares. Okay, so here's one particular little square. The edge lengths are delta x by delta y by delta z. Think about the point in the middle being the point x, y, z. And so the point in the middle of the top face would be x comma y comma z plus delta z over 2, and the one in the middle of the bottom face here would be x comma y comma z minus delta z over 2. Right? So what I'm going to do is I'm going to calculate the flux across the surface of the whole little cube there. I'm going to do top and bottom together, and then I'm going to do front and back together, and I'm going to do left and right together, maybe not in that order. But I'm thinking of front and back here, so it looks like the y-axis is coming in and out at me, and the x-axis is running sideways. So I'm calling left and right different x values. So the leftmost x value and the rightmost x value, where front and back are changes in y. So the back of y is there, and the front of y is here. And likewise, z, the lowest z is the bottom, and the highest z is the top. Okay. So notice the flux out of the top. Outward normals, so the k is upwards on the top. On the bottom, it's going to be minus k to go down, unit normal vectors here. In the x direction, I'd have an I sticking out, sorry, x is this way, so I sticking out here, minus I that way, and in the y direction, j is out, minus j is back. But focusing just on the top now, the flux out of the top is going to be the vector field dotted with k times that little bit of area. Now, essentially, as we do in any time we're doing an integral, I'm taking those little pieces, and each little piece I'm taking one particular piece of that, one particular point to plug in and evaluate, and essentially assume it's constant over the rest of that little piece. So I'm using the point x, y, z plus delta z over 2 as the point that I'm plugging in. But notice when you dot f with k, k is just a vector 0, 0, 1, so you just get the third component of r, sorry, or third component of f, which is r. So I have r with x, y, z plus delta z over 2 plugged in there, okay? And then times a little bit of surface area. Of course, a little bit of surface area is just delta x times delta y, okay? Likewise, the flux out of the bottom would be similar, except that you're now dotting with the outward vector on the bottom is minus k. So this is minus r evaluated x comma y comma z minus delta z over 2. So the total coming out of both the top and the bottom is just add those two up, add this and that. And notice I can factor out the delta x delta y to get this. But r of this thing minus r of that thing is just the change in r from the bottom to the top, right? So I'm going to just call that delta r. So the flux adding top and bottom is the change in the r value times the area, delta x delta y. But notice if I divide by delta z and multiply by delta z, then that delta z divided by, I need to move this over a little bit here. Oops, no, I need to move this over a little bit. The flux here is, well, that the delta r over delta z is essentially the partial derivative of r with respect to z. Notice x and y aren't changing from this point there to that point there. So you're only changing z, and you're looking at something close to the partial. And of course, as you take these squares, these cubes, smaller and smaller and smaller, that's going to be better and better approximated by the partial of r times dv. And the dv, of course, is just delta x, delta y, delta z. Likewise, in the other direction, in the x direction, the flux out of the left and right sides, the normal vector in the x direction would be I, which is 1, 0, 0, or in minus 1, 0, 0, depending on which side you're looking at. So you're not going to be getting r out of this dot product. You're going to be getting p. You're going to get the first component of f. So rather than f dotted with k, you're going to have f dotted with I. So it's going to be p at this point, where I'm changing the x's rather than the z's now. So this is x plus delta x over 2 and x minus delta x over 2. But of course, on this other side, you're going to have a minus I as your normal vector, so the minus sign comes there. When you add them together, you essentially get the partial of p with respect to x times dv. Likewise, in the y direction, you're going to get the partial of q with respect to y times dv. Adding them all up to get the flux over the whole cube, you get the partial of p with respect to x times dv plus partial of q with respect to y times dv plus the partial of r with respect to z times dv. If you factor out all the dv's, what you're left with is the divergence of f times dv. Now I can say what I wanted to do is I want to take each one of these little cubes, figure this out, and add them all up. Well, I can interpret this in two ways, because what this is a function evaluated at a particular point times a little bit of volume, and I'm doing that for each one of the cubes over this whole solid. Well, that's, by definition, a triple integral. So you're doing the triple integral over E of the divergence of f dv. But I wasn't doing a triple integral, I was doing surface integrals over the surface of each of those cubes. And so what I'm doing is now I'm adding up all those surface integrals. But each cube, well, cubes on the interior will be sharing faces with other cubes. So you got a cube here and you got a cube here, both sharing the same face. And so going back up to here, you know, this cube is using k as the normal vector for that top face. But if you had another cube sitting on top of that, then the outward normal for that cube would be minus k. So that face is having its surface integral done with one vector for the bottom cube and for the opposite vector for the top cube. And by just switching that vector around, you're going to change the sign of the result. So any two cubes that share a face, the surface integral over that face is going to be a net of 0, because you get it positive for one, you get it negative for the other. And so the only surfaces that don't cancel out are ones where you're on the edge of the region because you don't have another cube sitting on the outside. So you would be getting only the stuff that's on the boundary of the region E, and as you take those smaller and smaller cubes, you get a better and better approximation of the surface integral over the boundary of the region E. And so we have, what do we have? We have, that's just the surface integral of f dotted with ds over the boundary of E. And so that's the theorem, that this triple integral is equal to that surface integral. All right. We're going to need to do some examples, but I think we will save that for the next video.